Welcome to our introduction on Unit 4.2 on sources of magnetism. I want to start off by asking 4 questions. The first question is, what creates an electric field? And the answer is, as you know, any charged particle. So a single positive charge has an electric field all around it that points radially outward in all directions. That's a non-uniform field. If you had a sheet of positive charge near a sheet of negative charge, then you'd have an electric field that's more uniform. It starts to become non-uniform on the outside of the plates, but in between the plates of this parallel plate capacitor, the field is uniform. But any arrangement of electrostatic charge, or even moving charges, would create an electric field. As long as you have electric charge, you have electric field. The second question asks, what responds to an electric field? And the answer is, well, once again, any charged particle. So if I had that single positive charge that creates an electric field, and then I have near it some other negative charge sitting some distance r away from it, then the response is that that negative charge experiences a force of attraction, and that force of attraction we can calculate according to Coulomb's law, k q1 q2 over r squared. Actually, I'll get rid of the k, we'll call it 1 over 4 pi epsilon naught. That's the same thing as k, correct? Okay, or how about this? Any charged particle will respond to an electric field. So what if we had that uniform field that exists between the plates of the capacitor, and then the particle that responds to it, again, is an electron. So this time the electron is a charge in motion. The electron would not continue in a straight line. It would be attracted toward the positive plate, repelled by the negative plate, so the electron would curve and follow a parabolic path between the plates, and then once it leaves the plates, from there on it would continue in a straight line. And this is how a cathode ray tube operates. All right, so the answer to both of the questions, what creates an electric field and what responds to an electric field, are the same thing, any charged particle. Now, what responds to a magnetic field? What will experience a force when it's placed in a magnetic field? Charge in motion. So if we had, let's say, for example, a uniform magnetic field that pointed to the right, if you just place a positive charge in that magnetic field, then the force would be 0. But if that charge is in motion, well, then the force would still be 0. But that's because the motion lies parallel to the field. So when we say what responds, we say any charge in motion. I'll just add the note that the motion has to at least have a component that lies perpendicular to the magnetic field. So if this charged particle had a velocity, let's say, in that direction, then we can break the velocity vector into components. There's a component to the right, we'll call that v parallel. There's a component upward, we'll call that v perpendicular, and then we know that the magnetic force is found by multiplying the magnitude of the charge times the perpendicular component of the velocity times the strength of the field. Okay, so that leads us to our final question. What creates a magnetic field? So I wonder if you have a guess. If you're thinking like I'm thinking, maybe it goes something like this. What was true for electric fields might be true for magnetic fields. The same thing that creates the field is the same thing that responds to the field. Is that also true for magnetism? The answer is yeah. Charge in motion responds to a magnetic field, but it's also charge in motion that creates a magnetic field. So there are a couple of laws that we'll use, or formulas or equations, or however you want to state it. There are just a couple of ways we can state mathematically the way in which charged particles create magnetic fields. One of them goes something like this. The little bit of magnetism you get from having just a tiny bit of charge in motion. So let's say there's this little charge dq moving to the right with a velocity v. The little bit of magnetism produced at, let's just pick any point in space there, that little spot, we'll call that point P. The little bit of magnetic field at point P due to this charge in motion can be calculated according to a formula. But wait, before I state the formula, let me remind you of something. If I have just a little bit of positive charge dq and it's not in motion, and I'm just trying to figure out how strong the electric field is at this point P. Then I draw in a line and I measure the distance from my charge to the point in question as r. And then I make note that along that line, I can make a line that's just 1 unit long. Then I would call that r hat. How do we find the electric field at point P? Well, the little bit of electric field you get due to having a little bit of charge is equal to what? kq over r squared, right? Or 1 over 4 pi epsilon naught times dq over r squared. Be careful. Electric field's a vector quantity, so the way I make the right side of this equation also a vector, as long as I multiply by 1, I don't change the equation. So I'm going to multiply by 1 in the form of multiplying by a unit vector. And so all that tells me is that the direction of this electric field is exactly the same as the direction of this vector r hat. So the electric field points directly away from the charge. Okay, well, I tell you all that so that the equation I'm about to show you for magnetic field doesn't look too foreign. The little bit of magnetic field you get due to charge in motion, it's not equal to 1 over 4 pi epsilon, it's equal to mu over 4 pi. So epsilon naught we called permittivity. If I leave out the subscript 0, we just call it permittivity. If it has subscript 0, then we're implying that the material surrounding the charge is air or vacuum, and so we call it permittivity of free space. This new symbol mu naught is called permeability. And, well, if I leave the subscript off of it, we call it permeability. If I include the subscript, then I mean permeability of free space. Okay, so there's a similarity. The 4 pi shows up, and instead of permittivity in the denominator, we have permeability in the numerator. And then we still have a dq, and it's still divided by r squared, and there's still going to be an r hat in the equation. The only thing that's missing is, well, any charge creates an electric field, but charge has to be in motion to make a magnetic field. So velocity has to factor into this formula. Now here's the trick to this one, the direction of all this stuff. Oh, and by the way, what do I mean by r and r hat? So if I draw a line that connects the charge to the point in question, then that line is represents the distance r. And if I make a vector that's exactly 1 unit long along that line, then I call that one r hat. So anyway, r hat is a vector, velocity is a vector, and the resulting magnetic field is a vector. I've left something out. See, here I'm multiplying a vector times a scalar, and you can do that operation just fine, and what you get is the resulting vector for electric field lies parallel to the r hat vector. But here I'm multiplying one vector times another, and anytime we do that, we need to decide whether we're taking a dot product or a cross product, and it turns out, in this case, it's a cross product. So I'm going to write this again a little neater, and we'll say dB equals mu naught over 4 pi dq v cross r hat all divided by r squared. Now, if we just stated that without making the comparison to dE equals 1 over 4 pi epsilon naught dq over r squared r hat, I'm not sure this would convey as much meaning if we didn't bother to make the comparison, right? It's worth noting that these are both examples of an inverse squared law. So taking the cross product, there's a little bit of a challenge there. The question is, what's the direction of the magnetic field that results at point P? Well, I can tell you that little bit of magnetic field that we're calculating would point out of the page. But we'll get into the direction of all these vectors in another video. Let me just conclude this video by showing you one more similar form of this equation. Instead of having a single charge dq moving to the right with velocity v and trying to find the magnetic field at this point P, let's say we have a wire and current, conventional current I, flows to the right, and at some point that current, the amount of current that flows through that segment of the wire is the same as the amount of current through that segment of the wire. Current isn't lost as it flows through a wire. So if the whole wire has a length of L, I'll say that this little segment right here just has a length of ds. And maybe I want to know what's the magnetic field at this point P, right? Because after all, current in a wire is a form of charge in motion. So the formula isn't too different than the formula we had in this case. We say dB equals mu naught over 4 pi. Remember the rest of the equation, right? dq, the amount of charge, certainly should factor in. How far away you should factor in. It should factor in according to inverse squared law. But then the velocity also has to factor into it, so v. And to make this properly a vector, I need to take the cross product between v and, well, something that's really just equal to 1, but a vector that's equal to 1, right? The unit vector r hat. Okay, so what we get here is the little bit of magnetic field due to the current in the wire. If I measure the distance from the portion of the wire where the current's going to flow to the point in question, I call that r. If I make a vector 1 unit long along that line, I call it r hat. And in this case, the vector dB, which points out of the page, is equal to mu naught over 4 pi times I ds, where ds is a vector. I take the cross product between ds and r hat, and I divide it by r squared. So these two formulas are a way of expressing this idea that all magnetic field is created by charge in motion.